So good afternoon again, and we will continue our class. Today is chapter 2 already, and last week you have been introduced to chapter 1, Introduction to Digital Design, where you should know already what is digital design, why you need why digital design, and why you need to learn digital design. And you should know also what you will learn in this course, what and also what technology, what tools that we will use in this course. So in this chapter, chapter 2, is about the modeling of the digital circuit and digital system using what we call a hardware description language, or in short HDL, right? So we will learn in this course to model or to design our um, circuit, a digital circuit, using what we call a hardware description language, or in short is a programming language. But the language is for is used for describe the structure of the circuit or the behavior of the circuit, and not just like not like computer programming that you have learned before, for example C++. All right, so that one is not used for designing hardware. That one is used to program a microprocessor in your computer, all right, or program the microcontroller, for example Arduino and so on. That is computer programming, or what we call a high level language programming. But in this course we will learn the another type of language that we will use to model or describe the circuit. So we will use to describe the connection of the circuit, the structure of the circuit, or even the behavior of the circuit, right? So that is what we will learn in this course actually. So chapter 2 will introduce you to that language, the hardware description language. So what we will learn in chapter 2 is this. First thing is, of course, the fundamental of the language, or language fundamental, and later we will learn design flow and hardware modeling in HDL. All right, how we model the circuit in hardware description language. And next we will learn how to synthesize the design. All right, how the design is synthesis from the program that we write, or from the code that we write. For example, if we have this code, we should know, or we should be able to derive uh, the circuit that will be synthesized too. Synthesize is mean to translate from hardware description language to the uh, circuit. And the last one for this chapter is to design, to introduce you to what we call a hierarchical design methodology. Yeah, so in chapter 1, actually hierarchy design was introduced to you already last week, and in this chapter we will see how it is actually done in designing our circuit, right? So let's go to the first one, the language fundamental. So this is the language that we will learn throughout the course. So the hardware description language is a computer programming language that is used to describe the structure and behavior of digital hardware. Right, just like I said before, this is the language to describe, to model the hardware. There are two popular languages that available. The first one is Variloc Hdl, and the second one is VHDL, or very high speed hardware description language. Both are very useful in designing the digital hardware. But in our course, we will use the Variloc Hdl, which is very popular in the industry, right? So a little bit about Variloc Hdl. It is the IEEE standard, Institute of Electrical and Electronic Engineer standard, called 1364. 1995 was introduced back in 1995, and since then there are many upgraded version or standard available, and this is the standard that still being used until today. Yeah, 1364 2005, introduced in 2006. All right, and there are many references or books, textbook, and also from the internet that you can use to learn Verilog HDL, right? But this course we will go or we learn in what we call the systematic, in a systematic way to learn how to use Verilog to design our circuit. So in Verilog HDL, the gate is represented by indicating its functional name, input, and output. So this is one of the way in using Verilog, where we can describe our logic gate. So this is the logic gate that you have been introduced before in digital electronic. This is AND gate. So to describe an AND gate in Verilog is very easy, where if we have an AND gate and a two input AND gate like this, where we have A, B, and the output is Y. So to describe in Verilog is very easy, where we can write the AND. AND here means that this is AND gate, and in bracket need to have the output first, Y, and followed by comma, and the input AB, or you can have BA, no problem. The sequence is not doesn't matter. The sequence is doesn't matter for input, but the first one must be the output. All right, in this case it's Y. So this is AND gate, and Verilog is case sensitive. What is case sensitive means that capital and small letter is important. All right. So in this case, to describe an AND gate, you need to use small letter, small alphabet, A and D. And you cannot use big A, capital N, or any one of these is capital, cannot. Yeah. It is case sensitive. So if you use any other than this, for example, you have capital A, when you compile your design later on, you will get the error message, right? So remember, Verilog is case sensitive. And if we want to describe an OR gate, it is pretty straightforward. Yeah, you just have OR here, and again, this is a small letter, and you have your input first, Y, and follow by output first, and followed by the input AB or BA, right? Doesn't matter there. And for NOT gate, and of course for NOT gate or inverter, we only have one input and one output. So NOT, Z is the output, and we have the input X, right? Very easy to describe the gate, logic gate. And this is the general structure of the Verilog code. So normally our Verilog code later on will have something like this, all right, where so to start our code, we need to start with module. So in bold uh, in bold here means that this is the Variloc syntax. All right, and this one module name is can be any name. All right, means that your circuit name. Okay, uh, so but the name must be in one word. If so, if you have two words like this, make sure that you have something like this, underscore whatever. So you cannot have two words for the module name, and also you cannot start with number. All right, you need to start with alphabet. Okay, and in bracket is the port name, means that what are your inputs and what are your outputs. So you need to list your port here in the bracket, and followed by semicolon here, right? And here is the body of your module, all right, where the first part will be the declaration part, where you need to specify the signal or the input, output, or any internal wire or signal that you have. For example, you need to specify what is your input. In this case, input, you need to list all your input. The output, you need to list all your output. All right. And if you have any internal wire, you need to list all the wire. If you have any signal, here is the signal or variable. You need to use variable. So later we will see when to use the variable. And we need to list all the variable that we have. All here are the declaration. I forgot one actually here. Maybe I will update the lecture note. Yeah, here I should have another one. We call it parameter declaration. Okay, so we have another one which is the parameter, where we can represent any constant with a label. Yeah, later on we will see what is how to use this parameter. And after that is the body of our circuit description. All right, how do we want to describe our circuit? All right, we have what we call as assign a continuous statement. We will see later what is this: initial block or always block, gate instantiation or module instantiation. Gate is just a logic gate. That here is the logic gate, right? Uh, here is logic gate. So if we want to use logic gate in our design, so we can use what we call the gate instantiation. Module instantiation is means that we instantiate or we import uh, the other module, the design, into our design. All right, so that is called module instantiation. For example, adder, the adder module, we want to use adder in our design, so we can instantiate or import that adder in our design. So that is basically the Verilog. So later on we will see how to use these all. And again, after we finish everything here, we need to have this end module. This is a must. End module and done, right? So let's see a very easy example here, where we can describe this logic in Verilog. How to do that? So we can use what we call gate instantiation. Where we insert or use uh, the library, the gate and or not. This is the internal library of the Verilog, that we can use straight away. So we can use here gate instantiation. So in this case, we have module and the name is circuit X here, right? The name of the circuit, so can be any name, right? Depend on your design. And in the list here, in the bracket here, is the list of the port, right? Yeah, in this case, in the port we have the input and output port. Yeah, we have X1, we have S, we have X2, and we have another one is F. So all are listed here: X1, X2, S, and F. And we want to define our input here. Input is X1, and we have X2 also for input, and S also input. Output is F. Output is F. And we have internal wire. So this one, K, G, and H all are internal wire. So we need to declare as wire. So wire KGH, KGH here, KGH wire. And to describe this circuit is very easy. You can instantiate the gate. So the first gate will be the NOT gate, or maybe you can start with this gate. So the order here is not, it doesn't matter. All right, you can start with any gate that you want. So all of this will be execute concurrently, because we design the hardware, not the computer program, where it will execute in a sequence. This one for this one, later this one, this one, this one. Yes, that will be in computer programming. But in hardware, this one will be executed in parallel, all right, concurrent. So the uh, arrangement here is doesn't matter. So you can start with this OR gate first and followed by this one, or this one first, is doesn't matter. So in this case, let's start with this one, NOT. So NOT, the output will be the K, the input will be S, and this one you have N, the output will be G, and the input will be X1 and K. So K and X1, or X1 and K. And the second AND gate, you have output is H. The input is S and X2. And the last one is the OR gate. All right. So output F for this OR, and the input is G and H in AND module. So this will represent this circuit. All right. So when we want to design this in hardware, all right, so this is one of the way. We have many ways. Later on we will see, right? This is the second example. The concept is the same, where we have the circuit number 2. The name is X also, circuit X also. We have input X1, X2, S1, S3, X2, X4, X1, X2, X3, X4, and the output is F, GH, F, GH. Input here, output is this. We have internal wire Z1 to Z4, Z1, Z2, Z3, Z4, and we can see that this is for this gate, Z1, X1, X3, and this one is for this gate, Z2, X2, X4. This one O is for this one, X1, X1, and this is new one. All right, because we don't want to describe these NOT gate, we can actually describe implicitly here, where we use this symbol to represent NOT. All right, so we can do that also. Means that this signal is inverted. X3 is inverted before we go to this gate. Right, we can use this one also, rather than using NOT. Right. So for this one, XOR number 2, so we have Z4, not X2, which is this one, not X2, and X4, and we have this, and this is the N, and for this one, H, Z3, here, Z4, H, Z3, Z4, yes, this one, or this is the gate, FGH, FGH. This one is G, this O, GZ1, Z2, right? So this will be synthesized into this circuit. Very easy. So that is the first and second Variloc program or Variloc code for you. So which is very easy. And now we want to use even further, because this one when we look at this, all right, this way, uh, to design the circuit this way using what we call netlist like this, or gate instantiation like this. So you need to have the circuit like this, and you need to label all the signal here, the wire here, and then you write the code. What if you don't have the circuit? All right, and normally when we want to design a complex circuit, we don't have the circuit, we only have the behavior or specification of the circuit. Now, if we don't have this circuit, can we use this? Of course cannot. So Variloc offer another features that we can describe our circuit using behavior of the circuit. For example, if we have this input and we describe our circuit, the output should be like this. All right, input like this, output like this. Tell the computer, and the computer will generate the circuit for us. Or we can even using the Boolean equation to uh, to 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 use computer, write the Boolean equation and use the computer to generate the circuit for us. Right? Later on we will see. Now, let's see what we need to know in order to write or to 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 have a good code, to write a good code. First is sign value and numbers in Variloc, how we represent numbers in Variloc. All right, so Variloc support scalar nets and variable that represent individual signal or vector. So we can have individual signal and or a group of signal, we call it vector, and can be or can have 4 possible values, right? So when you write 0 in Variloc, that means logic 0, logic 0. If you write 1 in Variloc, that means logic 1. And if you write Z, if the signal is equal to Z, for example, and that means 3 state. 3 state in here is means high impedance. High impedance means not connected. All right, Z. If you learn in circuit analysis course, when your circuit have no connection at all, means that the potential here will be in high impedance, right? So the label is Z, and X is unknown or don't care, all right? So if we have unknown value or don't care, we use X in our program. The format of representing the number in Variloc is like this. The first field is the size of your number, and the second field is the what we call a radic. A radic means that the base, whether your number is decimal, whether your number is hexadecimal or binary. All right, that is called radic, and the number followed by the number. All right, so the size is in bit, in bit, whether your data or your signal is 1 bit, 2 bit, 3 bit, or any other bit. That is the size. So radic here, if you have D, means that is that number. Here the number will be the decimal number. If you write B, that number will be the binary number. If you write H, the number will be hexadecimal. If you write O, the number will be octal. Okay, so these numbers are very important in computer, especially binary and hexadecimal. Octal, we actually rarely use octal in digital design, right? So digital, because digital is 0 and 1, so binary is very important. And hexadecimal is a good representation of binary number, because binary number, in binary, if we want to write a binary number, for example 8 bit, you need to write 8 digit, right? So to make it simple, what we do is we use hexadecimal, where 8 bit we only use 2 hexadigit, instead of 8 binary digit. That's why we use hexadecimal a lot in computer and digital design. Okay, so this is some of the example that to show you how to write the number in Verilog. So if you write 0, right, because the Variloc compiler is actually very sophisticated, very good enough already. If you write 0, it will by default it will treat the number as decimal, or you write 9, for example, so it will treat the number as decimal. So normally, if decimal, no need to write this way. The computer or the compiler will understand where that will be decimal number. For example, if we put 10, or we write 10 in the Verilog, so that means that this number is decimal 10. But if we write this way, 2, this is the radic binary 10, means that our number is 2 bit and the value is 10, right? Means 10 is 2 in decimal. If we write 5, 10 and H, so this is but not binary but hexadecimal. 10 hexadecimal means 0001000. Yeah, but 5 bit. By 5 bit means that the if we look at this, we have 5 bit. What is it? 10, right? So means that we have 5. Our number is 5 bit. 1, 2, 3, 4, 5. 3, 4, 5. And this 0 is 4-bit hexadecimal binary. This is in binary, 0, 0, 0, 0 represent this. And we have 1. Actually, in hexadecimal, it should be like this. But because we only say that our number is 5 bit, so we only count this. Okay, that is the meaning of this 5, 10 means that in decimal is 16 in decimal. And if we write like this way, 4, this means that our number is 4 bit and this is in binary, so 0, 1, 0, 0 means that this is binary 0, 1, 0, 0, and in decimal should be 4. Okay, very easy. Now go to the next parameter. What is parameter? Parameter is normally used to assign uh, what we call an identifier or constant, to a number. So for example, n we assign with 4 here, parameter n equal to 4. Later on, when we want to use 4, we just can replace with n. Or for example, as 0 is equal to 0, 0 in binary. So later on, when we want to use this number, we can replace by S0, or S1 if we set parameter S1 as 0, 1 in binary. So later on, when we want to use this number, we can use S1 instead, right? So that is the use of parameter. Very important, where when we design uh, a repeated circuit or very big circuit later on. For example, the size, our uh, initial design is the size is 4-bit. Later on, we want to change to 8-bit, for example. So we can use this one. And first we set to 4, means that everything after this is 4-bit. But when we want to change, or we want to improve our design in the future, we want to change to 8-bit or even bigger, we can change this number only, and everything after this, when that represented by n been changed to 8 or 16 or even bigger, right? And next data type. So next data type is actually you have been introduced before. The wire is actually in in the group of net data type. Wire X, Y, Z. This is actually the internal wire like this. And we have another one, tree. Tree is the three-state uh, buffer, where, for example, X, we don't want to connect to anything or floating, so we can use tree. And in the design later on, we rarely use this tree, but sometimes you may need it, right? Depend on the design. Operator. So operator is very important, where we will use a lot later on, especially in describing the Boolean equation or uh, arithmetic operation, right? So we will use the operator. So for example, when we write C equal to this symbol and A in Variloc, so this is actually C equal to not A, right? And if we write C equal to A and symbol and B, this means that C is equal to A and B, right? So these all are the operator that we will use a lot in our program, our code later on. All right, so you can always refer back to this, or you can get from the internet. There are many. Okay, so we have the first one is bitwise, means that the operation is operated bit by bit, bitwise. For example, we want to have like this, C equal to not A. So if A is 1 bit, so not A 1 bit, and A and B, and so on and so forth. This is AND, this is OR, this is OR. All right. If we use this, for example, it will synthesize, will be synthesized to AND gate. If you want OR gate, so you can use this. If you want an XOR gate, so this is the symbol. If you want the XNOR, you can use this one or this one, either one, both are correct. And you can see that here is this column is number of operand. What is mean by number of operand? Operand is this. For example, this one. This is called operand. This is called operand. So we will see that if the operation is not like this, so means that the operand is only one, A. That's why we have 1 here. But if you use n, all right, the number of operand must be 2. See, we have 2, right? If you use OR, the number of operand must be 2 also. XOR must be 2. XNOR also must be 2. And next group is the logical group. This is for NOT also, but we're not using this in Boolean equation later on, but we will use in testing. For example, Is it A? Is it not A? Is it not B or not C? All right, we want to test something. Or if A equal to A and B equal to 1 or not, A and B equal to 0 or not. All right, this we call logical. And here again, number of operand is the same. Not is 1, N is 2, or double, what do you call this symbol, right? Or this is interesting, reduction group. So N, reduction N, but we can see that 1, all right, only 1 operand means that only N but 1. What we know is that N must be 2 operand, right? Or must be 2 operand. But in reduction, this is 1 operand. What is 1 operand means here? And what is reduction here? Reduction is actually something like this. For example, our A, or we want to do this. This is F, the output. And the input is A, but our A is in the form of vector where we have A0 and A1. Right? So in Variloc, we can write like this: F equal to right. When we write like this, we will get this gate, and this is A0 and A1. Right? But of course, before that, we need to declare A as a vector. We will learn how to do that later on. So we will see that here the number of operand is 1. Okay, and that is the meaning of this. So we have reduction NAND, reduction OR, NOR, XOR, XNOR, and so on. Arithmetic. So if we use plus, means that we add the number, and when we add the number, means that we infer, or we create an adder, for our design. When we use minus here, this is subtraction, so the subtractor. When you use 1, minus also, this is means second complement, and look at the number of operand 1. This means that something like this. When you write F equal to minus A, means that this is the second complement of A, or minus A, right? And the number of operand is 1. Multiplication is this, division is this. This is relation, so we can test also if, for example, greater than, less than, greater than or equal, less than or equal, right? This is logical equality, right? If A equal to B, we do this. Not equal is this. This is shift right, or right shift. This is left shift. Here is concatenation, a little bit correction here. Concatenation is like this. We have curly bracket inside, and like this. Means that concatenation is used to combine the signal. All right. For example, we have signal A and signal B. So we want to combine these two signals. So we can have something like this. C equal to A, B, This is called concatenation. So what we will have is that the original wire is A and B. When we do that, we will rename this wire, or we can use later on this wire as C, where the first one will be the either C0 or C1. This one will be C0, this one will be C1. Means that the C must be 2-bit, the size, yeah? C1 here. Okay, that is the meaning of concatenation. And next is replication. Replication means that we replicate the signal. Right. For example, we want to replicate the A signal, so we can do something like this: 3 times A So what we can get later on is A. That is replication. And the last one is condition. Condition we will see in the next example. I will show you what is condition. Condition normally we will use to create a multiplexer. Okay, so that will be the operator that we will use most of this, and no need to memorize this. Yeah, so you can open the books anytime. But the important thing is that you should be able to use this operator in order to write a good code. Now, looks at this. Always an initial block. We are now, if we go back a little bit here, here initial block, always block. So we have learned already: input, output, wire, rect, not yet, integer, not yet, parameter, yes, learned already, assign, not yet, gate instantiation, learned already, module, not yet. Now is always block and initial block. Always block is a construct that contains one or more procedural sequential statement. When multiple statement included in always block, the statement begin and end are used. For example, this. While the sensitivity list is a list of signals that directly affect the output generated by always block. So this we call sensitivity list. So what is exactly always block? Always block is one of the method or the way to describe the circuit in Variloc. Before that, we learned how to describe using gate instantiation. Now, the always block is a very powerful method to generate the circuit, especially using behavior of the circuit. And it is called the procedural assignment or sequential assignment. Right? So what is it? It means that the compiler, will evaluate each of the assignment here or statement here in sequence. Means that it will look this first and then do this and then do this in sequence. All right. This is different from the previous one where it is executed or evaluate in at the same time or simultaneously. All right, but in always block, the result for this will affect this. Yeah, will affect this. So normally the Variloc compiler will read all the statement, evaluate all the statement until the end, then it will synthesize or generate the circuit based on the statement that we write, and it is written in behavioral manner, the behavior of the circuit. And also we can use the uh, uh, Boolean equation. Boolean equation is the behavior also of the circuit. All right. For example, we have two statements here. If you have two statements, means that the block will start here and end here. So the block need to start with begin and end with end. And this is the first statement where s equal to x. This is x or y, and c is equal to x and y. Right. So we can describe our circuit using this. This. So this will be synthesized into a circuit, yeah, x or y, very easy, where we have x, y, we have x or, and then we have s, right? And then another one is the AND gate. The output is c. Okay, so that code will be synthesized to this circuit. Initial block or initial construct is used for simulation purpose. So for initial block, so we have initial block, always block. Always block, yes, we used to describe, to design our circuit. But initial block, actually, we not used to design the circuit. We will use in simulation purpose later on. Right? For example, when we want to design our circuit, of course, we have the specification. After specification, we derive our circuit. We write the code, and we want to know later on, after we have our code already, we want to know whether um, our code, our design is correct or not. So we will need to do simulation. All right. So in the simulation, we will write another code. We call the test bench code. All right, to test our design whether it is correct or not. Okay. So the initial block will be used in simulation code, right? Not in the design. Next, assign. Assign statement is used to make continuous statement. Continuous statement is another name is the concurrent statement. Means that when we use assign, or we want to use Boolean equation, right, without using always block. Before this, we use Boolean equation, all right, but this Boolean equation is inside what we call the always block. But sometimes we don't want to use always block, so we need to use assign keyword to do that. For example, assign f equal to a and b or c. Assign out equal to in 0 plus. This plus means add, not or. Or in Verilog is this. Plus here means add, adder. All right, means that in 0 plus in 1. And these two statements will be executed concurrently or simultaneously. That's why we call this as continuous assignment statement or concurrent statement. This is called assign statement. Variable. Variable in Verilog, we have two types. One is rect and another one is integer. So rect here is don't confuse with register. And this rect is not register, right? It will not synthesize to into a register, but it is a variable, actually a signal. All right. And integer also a variable in Variloc. So let's look at this code. This code using sequential assignment. So now remember, we have two kind of assignment. First one is continuous assignment. All right, continuous assignment means that we use the keyword assign in our design. For example, we have the Boolean equation, and we describe our circuit using Boolean equation. So we have G equal to this, H equal to this, F equal to this, and we use the assign keyword. All right. So by using that, we call this as continuous assignment, and all of these will be evaluated or executed simultaneously or at the same time. All right. That is continuous assignment. The second one is called sequential assignment. So sequential assignment normally used for uh, describe our circuit using behavior manner, yeah, using behavioral. So to use sequential assignment, you need to use always block, right? So this is the always block, and let's see how to do that. So in this code, we have input x, x1, x2, s, and we have one output f. So our circuit will be something like this. Let's So our circuit will be something like this, where we have input, three input, and one output, right? And what are the three input? X1, x2. So we have x1, x2, and we have s, and we have one f. Okay, and we don't know what is inside. So the inside here is actually this. And this is described by this behavior. So the behavior is this. If s equal to 0, the output is f is equal to x1. But if s equal to 1, or else here, the output f will be equal to x2. So this is behavior. We don't have the circuit, but we know the behavior is something like this. So we can maybe create the truth table for this behavior, right? So we have x1, we have x, we have x1, we have x2, and we have f for the output. And let's write the value for input. So we have three input, so we should have up to 8 possibilities. Start with 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, number 3, number 4, 0, 1, 1, right, up to 7, 1, 1, 1. And let's see, the behavior is like this. If s equal to 0, if s equal to 0, the output Okay? This is s equal to 0, yeah, not s. Means that s equal to 0. F must be equal to x1. So x1 will be this. So f should follow this value. And if s equal to 1, f should be equal to this, which is 0, 1, 0, 1. So what is this? So we can actually derive the Boolean equation. And this is actually a behavior of a multiplexer. Yeah, we will learn multiplexer in the next chapter. So this is basically something like this. X1, X2. A multiplexer. X1, X2, and F. Okay. So you see, when we want a multiplexer, and we know already the behavior of this multiplexer is if s equal to 0, so the value of f should be equal to x1. If s equal to 1, the value of f should be equal to x2. Okay, so we don't have the circuit, we don't have the Boolean equation, but we can write in the Variloc the behavior of it. And this behavior must be written in sequential assignment or using the always block like this. So the Variloc compiler will compile this code and give you a multiplexer. This without knowing or without having this truth table and also the Boolean equation and also the circuit. We don't have, but we know the behavior of this circuit, and we write the description based on the behavior of the circuit. Right. So this is very powerful tools that allow you to create a very complicated circuit later on. All right, because normally in design we don't have the circuit, but we want to design the circuit. We only have the specification. All right, how the circuit behave. And the good thing is that we can describe that behavior in Verilog and let the computer to generate the circuit for us. Okay, so that will be the good or the important thing. And of course, we as a designer, we must know also if we write the code this way, the output, the result must be a multiplexer. That's why we need to learn the theory. And one more important thing is that observe this. When we use always block, okay, when we use always block and we want to assign a value into this f, and f is output, but f is inside the always block. All right, whenever you use always block to assign a value to variables, because this is not wire or port anymore, this f, yeah. When you use always block, this will be a variable. So you must declare f as a variable as well. And in Verilog, a variable is rect, right? That's why you have rect f here. If you don't have this, when you compile your design, you will have an error message from the compiler asking you to have this data type. F need to declare as rect data type as well. Okay, and of course F is the output, and you need to declare as F as the output as well. Right? That is the use of rect. Later on we will see the use of integer. Okay. Right, before we go to the modeling style, we are a little bit more than 1 hour already. Can we have a little break, about 10 minutes before we come back? Okay, so we have 10 minutes break, come back at 3:23.